use thermostatic resins like silicone, vinyl ester, epoxy, phenolic, polyester, etc. materials. This is the diagram of transfer molding. Here we can see that there is a plunger and there is a transfer pot. The material which we want to mold is kept in the transfer pot. So the material is also preheated. Uh, so we can దాన్ని హీట్ చేయాల్సిన అవసరం లేదు మళ్ళీ. సో ద ప్లంగర్ అనేది ఏం చేస్తుందంటే అక్కడ ఉన్న ప్లాస్టిక్ మెటీరియల్ ని క్రష్ చేస్తుంది, దాన్ని మోల్డ్ క్యావిటీలోకి పంపిస్తుంది. దాని తర్వాత అది హాట్ గా ఉంటుంది. సో తర్వాత ఇజెక్షన్ పిన్ ద్వారా దాంట్లోకి మెటాలిక్ వైర్ పాస్ చేస్తాం. అది ఏం చేస్తుందంటే దాని చుట్టూరు ప్లాస్టిక్ కోటింగ్ అనేది ఇస్తుంది. దీనికి హీటర్స్ అనేవి అవసరం లేదు. బయటకు వచ్చిన తర్వాత కూడా హాట్ గానే ఉంటది కాబట్టి దాన్ని కూల్ చేసుకొని కేబుల్స్ కింద వాటి కింద వాడుకుంటారు. దీంట్లో జరిగే మెయిన్ ప్రాసెస్ ఇది. దీని యొక్క అడ్వాంటేజెస్ కి వచ్చేసరికి సింపుల్ ప్రొడక్షన్ సైకిల్ అండ్ ఫాస్ట్ ప్రాసెస్. మనకి తక్కువ టైంలో ఎక్కువ ప్లాస్టిక్ అనేది బయటికి ప్రొడ్యూస్ చేసుకోవచ్చు. హీట్ అనేది రిక్వైర్ అవసరం లేదు, ఎందుకంటే ముందర చెప్పాను దీన్ని ముందరగానే హీట్ చేసేసిన తర్వాతే మనం క్రషింగ్ అనేది చేస్తారు. డిసడ్వాంటేజెస్ కి వచ్చేసరికి వేస్టేజ్ ఆఫ్ మెటీరియల్ ఇస్ మోర్. మనకి ఈ ప్లాస్టిక్ అనేది వేస్ట్ అయిపోయిన తర్వాత థెర్మోసెటిక్ రెసిన్స్ అనేవి నాట్ రీయూజబుల్, కాబట్టి మనకి వేస్టేజ్ ఆఫ్ మెటీరియల్ అనేది చాలా ఎక్కువగా ఉంటుంది. ప్రొడక్షన్ రేట్ కూడా స్లోగా ఉంటుంది. దేనికంటే ఇంజెక్షన్ మోల్డింగ్ కన్నా. ఇంజెక్షన్ మోల్డింగ్ లో ఏం చేస్తామంటే మనం మిషన్ లోకి వెళ్ళిన తర్వాత మెటీరియల్ అనేది హీట్ చేసి తర్వాత క్రష్ చేస్తాం, కానీ మనకి ఇక్కడ అంత యూజ్ లేదు కాబట్టి ప్రొడక్షన్ రేట్ అనేది స్లోగా ఉంటుంది. మనం దీనికి ఎంత హై ప్రెషర్ అనేది యూజ్ చేస్తామో మనకి క్వాలిటీ, ప్లాస్టిక్ యొక్క క్వాలిటీ అంత పర్ఫెక్ట్ గా వస్తుంది. దీని యొక్క అప్లికేషన్స్ వచ్చేసరికి నెక్స్ట్ న్యాచురల్ గ్యాస్ ఇండస్ట్రీస్ లోను, హైడ్రాలిక్ ఇండస్ట్రీస్ లోను, ఏరోస్పేస్ అండ్ ఆటోమొబైల్ పార్ట్స్ లోను బాగా యూజ్ చేస్తారు. చాలా స్ట్రాంగ్ మెటీరియల్స్ కింద మౌల్డ్ చేసుకొని ఈ ఇండస్ట్రీస్ లో అనేవి వాడతారు. నెక్స్ట్ వచ్చేసరికి ఎక్స్ట్రషన్ మోల్డింగ్. ఎక్స్ట్రషన్ మోల్డింగ్ అంటే ఇట్ ఈస్ ఎ మ్యానుఫ్యాక్చరింగ్ ప్రాసెస్ యూజ్డ్ టు మేక్ పైప్స్, డ్రింకింగ్ స్ట్రాస్, కర్టెన్ ట్రాక్స్, రాడ్స్ అండ్ ఫైబర్స్. మెయిన్ గా వీటిని ఉపయోగించుకోవడానికి కారణం ఏంటంటే మనకి డైలీ యూసేజ్ ప్లాస్టిక్ అనేది చాలా ఎక్కువగా అవసరం కాబట్టి ఇవన్నీ ఎక్స్ట్రషన్ మోల్డింగ్ ద్వారా ఇవన్నీ మనం తయారు చేసుకుంటాం. ఎక్స్ట్రషన్ మోల్డింగ్ ఇస్ అప్లికబుల్ టు థెర్మోప్లాస్టిక్స్ ఓన్లీ. థెర్మోప్లాస్టిక్స్ ని మాత్రమే చేయగలం. ఎగ్జాంపుల్ పాలిథిన్, పాలిప్రొపెలిన్, పాలివినైల్ క్లోరైడ్, పాలిస్టర్స్, పాలిస్టైరిన్ అండ్ ఎక్సెట్రా. దీని యొక్క డయాగ్రామ్ వచ్చేసరికి ఇది. ఇక్కడ మనం చూసినట్టయితే ఇక్కడ హోపర్ అనేది ఉంటుంది. మనకు కావాల్సిన ప్లాస్టిక్ మెటీరియల్ ఏదైతే ఉంటుందో ఈ హోపర్ ద్వారా లోపలికి ఇస్తాం. అది ఇచ్చిన తర్వాత ఇక్కడ ఒక స్క్రూ కన్వేయర్ ఉంటుంది. ఈ స్క్రూ కన్వేయర్ ద్వారా ఈ ప్లాస్టిక్ అనేది మౌల్డ్ అవుతుంది అనమాట. దీని యొక్క హీటర్స్ వల్ల ఆ ప్లాస్టిక్ అనేది చాలా సాఫ్ట్ గా అవుతుంది. ఇందులో మనకి యూస్ఫుల్ పాయింట్ ఏంటంటే ఈ ప్లాస్టిక్ ని మనం ఎన్నిసార్లైనా హీట్ చేయొచ్చు, ఎన్నిసార్లైనా కూల్ చేయొచ్చు. దానివల్ల ప్లాస్టిక్ వచ్చే నష్టం కూడా ఏమీ ఉండదు. సో ఇక్కడ ఉన్న స్క్రూ కన్వేయర్ ద్వారా ఆ ప్లాస్టిక్ అనేది మౌల్డ్ అవుతుంది. మౌల్డ్ అయిన తర్వాత ఇక్కడ మెటాలిక్ వైర్ ని ఇంట్రడ్యూస్ చేస్తే దీన్ని కేబుల్స్ ద్వారా బయటకు వస్తుంది. ఇది మనకి లాంగ్ చైన్ ప్రాసెస్ అనుకోవచ్చు. దీంట్లో చాలా పెద్ద పెద్ద ఆర్టికల్స్ అనేవి అన్ని బయటకు మనం కంటిన్యూస్ గా ప్రొడక్షన్ అనేది తీసుకోవచ్చు. ఇది దీని యొక్క మెయిన్ ప్రాసెస్. సో నెక్స్ట్ అడ్వాంటేజెస్ కి వచ్చేసరికి ఇట్ ఈస్ లో కాస్ట్ రిలేటివ్ టు అదర్ మోల్డింగ్ ప్రాసెసెస్. చాలా తక్కువ ఖర్చుతోనే ఈ మోల్డింగ్ ప్రాసెస్ అనేది చేసేయచ్చు. ఇట్ ఈస్ మోస్ట్ ఎఫిషియంట్ అండ్ ర్యాపిడ్ మెథడ్ ఫర్ ప్రొడ్యూసింగ్ లాంగ్ కంటిన్యూస్ ఆర్టికల్స్. మనకి కంటిన్యూస్ గా కేబుల్ వైర్స్ అనేవి చాలా పొడవుగా ఇన్ మీటర్స్, కిలోమీటర్స్ ఎంత పెద్దగా కావాలనుకున్నా తీసుకోవచ్చు. ఎక్స్ట్రషన్ మోల్డింగ్ ప్రొవైడ్స్ కన్సిడరబుల్ ఫ్లెక్సిబిలిటీ ఇన్ మ్యానుఫ్యాక్చరింగ్ ప్రొడక్ట్స్. మనకి ఇది ఈ ప్లాస్టిక్ వైర్ అనేది బయటకు వచ్చిన తర్వాత హాట్ గా ఉండడం వల్ల ఫ్లెక్సిబిలిటీ అనేది చాలా ఎక్కువగా ఉంటది. కాబట్టి దాన్ని వాటర్ తో కూల్ చేస్తారు. కూల్ చేసి యూసేజ్ చేసుకుంటారు. నెక్స్ట్ డిసడ్వాంటేజెస్. ఇట్ కెన్ బి యూజ్డ్ ఫర్ లీనియర్ పాలిమర్స్ ఓన్లీ. ఇందాక ఎగ్జాంపుల్స్ చెప్పాను కదా, పాలిస్టైరిన్, పాలిప్రొపెలిన్, పాలివినైల్ క్లోరైడ్, వీటిని మాత్రమే యూజ్ చేయగలం, మిగతావి యూజ్ చేయలేం. వెన్ ద హాట్ ప్లాస్టిక్ ఎగ్జిస్ట్ త్రూ ద ఎక్స్ట్రూడర్ ఇట్ ఫ్రీక్వెంట్లీ ఎక్స్పాండ్స్. చెప్పాను, దానికి ఉన్న ఫ్లెక్సిబిలిటీ ప్రాపర్టీ వల్ల సాగిపోతూ ఉంటది బయటికి రాగానే. కాబట్టి దాన్ని ఎంత ఫాస్ట్ గా కూల్ చేస్తే అంత నీట్ గా ప్లాస్టిక్ అనేది బయటకు వస్తుంది. నెక్స్ట్ అప్లికేషన్స్, ఇవి కేబుల్ వైర్స్ కింద, టూత్ పేస్ట్ ట్యూబ్స్ కింద, డ్రింకింగ్ స్ట్రాస్ కింద మనం యూసేజ్ చేసుకుంటాం. థ్యాంక్ యూ. థ్యాంక్ యూ సార్.
Any questions? Okay. We will go to next presentation.
Okay. Next, number 17, Harshita.
Yes, sir. Sir, is my screen sharing? Hello?
Yeah.
Sir, is my screen sharing?
Yes. Yeah, it is visible.
Yes. Good morning, everyone. I am Harshita. My topic is corrosion and chemical corrosion mechanism. Coming to definition of corrosion, the process of destruction or deterioration of metals or its alloys by chemical or electrochemical attack to its environment starting at its surface is called corrosion. Corrosion starts at the surface of any metal. Example, rusting of iron, formation of blue-green film on copper or bronze, tarnishing of silver. Next, initially metals, when we are extracting them, they occur in combined states as oxides, hydroxides, etc. When we want pure metal, we extract them, but metals have tendency to be stable at their combined form, so they undergo oxidation and form metallic compound. This process is nothing but corrosion. So metal always tends to corrode and go back to the combined state. If by reduction we get metallic compound, they combined state to the metal. So reverse process of extracting metal from metallic compound is corrosion. Generally, causes of corrosion, metals are stable only in their compound state, so they get back to their original state by the means of corrosion. Less energy states, metallic compounds are more stable than higher energy states. Higher energy state means metals, low energy state means their combined forms. Types of corrosion. Corrosion of the metals occurs by the attack of surrounding environment on the surface of the metals. Generally, these are of two ways: dry corrosion and wet corrosion. Dry corrosion is also known as chemical corrosion. Wet corrosion is electrochemical corrosion. As my topic is dry corrosion, I am going to explain dry corrosion. This type of corrosion occurs mainly through the direct chemical action of atmospheric gases such as oxygen, halogens, etc. on anhydrous inorganic liquids with metal surfaces in immediate proximation. This type of corrosion, dry corrosion, mainly occurs direct chemical action of atmospheric gases, those gases on metal surfaces with immediate proximation. The extent of corrosion depends on two qualities: the chemical affinity between the corrosive environment and solid metals. Chemical affinity base చేసుకొని కూడా base చేసుకొని corrosion extent ని చూస్తాము. The ability of action product on metal surface to form a protective film. The formed protective film also decides the ability of reaction between the metal surface and the environment. There are three main types of corrosion. those oxidation corrosion, corrosion by other gases, and liquid material corrosion. Coming to oxidation corrosion, it occurs by the direct action of oxygen at low temperature on alkali and alkaline earth metals. Direct action of oxygen. Oxygen when metal when reacted with oxygen in environment like alkali and alkaline earth metals, it is a direct oxidation where at low temperature, high temperature they are almost oxidized. Here reactions metal when oxidized they form metal ions and some number of n electrons. When oxygen O minus to which is reduction, these metal ions and oxygen ions form metallic oxide which is known as corrosion mechanism. When we come to mechanism, oxidation occurs first at the surface of the metal and the resulting metal oxide scale forms a barrier that tends to restrict further oxidation. When firstly when surface of the metal is exposed to environment, the oxygen present in the air uh, forms a barrier near the metallic oxide, which forms a barrier that restricts oxidation. Further oxidation to continue, either the metal must diffuse outwards or the scale to the through the scale to the surface, or the oxygen must diffuse inwards. Means when there is a metal oxide barrier between the environment air and metallic surface, either the metal should diffuse outwards or oxygen should diffuse inwards to further oxidation or further corrosion. Both diffused ions meet together to form metallic oxide. Metallic oxide layer which further the nature of the oxide forms an important role in oxidation process, and metallic oxide forms barrier that tends to restrict further oxidation. The nature of the oxide also plays an important role. We'll see later. The oxidation starts, a thin layer of oxide is formed on the metal surface, and the nature of this film decides the further action. See here, metal plus oxygen, which gives metallic oxide near the surface of the metal, which is corrosion product. That film decides whether the metal should further oxide, corrode or not. This film is of four types generally: unstable oxide, stable porous oxide, volatile oxide layer. First, unstable oxide. If the oxide layer is formed and decomposed back into metal and oxygen. So, film, if the film is unstable oxide, it will decompose back into metal and oxygen. When metal is exposed to air, with the reaction of oxygen in air, it forms an unstable metal oxide on the surface of the metal. When it decomposes, it goes back into oxygen and metal. So, it has more effective to corrode easily. So, oxygen and metal get separated in unstable oxide. Stable oxide. Stable non-porous oxide layer is adhered tightly to the metal surface and forms impervious to nature. When the film is non-stable porous oxide, it sticks tightly to the surface of the metal, so it prevents the metal surface from any further contact with atmospheric oxygen. So it does not allow atmospheric oxygen to react with the metal anymore. Such film behaves as a protective coating in nature, thereby shielding the metal surface. Aluminium, tin, lead, copper, etc. are examples for this. Metal oxide films are stable, adherent, non-porous, and impervious in nature. Consequently, further oxidation is prevented. So, stable oxide layer prevents the further oxidation of the metal. Stable porous oxide. Stable porous oxide layers have pores and cracks. In such cases, atmospheric oxygen has access to the underlying surface of the metal through the pores or cracks of the layer. Thereby, corrosion continues unobstructed till the entire metal is converted into oxide. These stable porous oxide have small pores from which they can atmospheric air can react with the metal. It stop until it does not stop until the metal gets fully corroded. That means the metal is completely converted into oxide. Alkali earth metal oxide layers. Further attack will go on continues from these porous or cracks. Volatile oxide layer. Volatile oxide layer volatiles as soon as it forms. Means it disappears. Volatile oxide layer, the layer which is formed will disappear as soon as it forms, thereby leaving underlying metal surface exposed for further attack. This causes rapid and continuous corrosion. Continuous corrosion will happen, leading to severe corrosion. Example, molybdenum oxide is volatile. Molybdenum, when reacted with atmospheric oxygen, forms a volatile metal oxide which disappears immediately, and fresh surface of molybdenum will expose to the air. Pilling Birchwood rule. According to Pilling and Birchwood, if the volume of the oxide layer is more than volume of the metal, the oxide layer is non-porous and hence protects the metals. If the volume of the oxide is more than volume of the metal, oxide layer, the oxide layer is non-porous and hence protects metal. If the volume of the oxide layer is less than volume of the metal, the oxide layer is porous and hence non-protective because it cannot prevent the excess of oxygen to the fresh metal below the oxide layer. Formula is given there. Volume of the metal Pilling Birchwood rule is volume of the metal oxide layer by volume of the metal is greater than 1, it is non-porous, and it is less than 1, it is porous. So according to this also we can say whether a metal can corrode easily or not by this volume. If you know the volume of the metal oxide layer and the metal, we can know that. Coming to corrosion by other gases, the extent of corrosive effect depends mainly on the chemical affinity, as we discussed before, between the metal and the gases involved. If the film formed is protective and non-porous, the extent of the intensity of attack decreases because the film formed protects the metal from further effect. If the film formed is non-protective and porous, the surface of the whole metal is gradually destroyed by corrosion. Example, dry chlorine gas. Chlorine gas attacks on thin forming volatile SnCl form. Liquid metal corrosion. It is due to chemical action of flowing liquid metal at high temperature on solid metal or alloy. It is due to chemical action of flowing liquid on metal at high temperatures. Such corrosion has been found to occur in devices used for nuclear power. The corrosion reaction involves either dissolution of liquid metal by a solid metal. This corrosion occurs by if flowing liquid dissolves with the solid metal present under it. Internal penetration of liquid metal into the solid metal. If solid metal have some pores or holes, something, when liquid goes inside, the metal have tendency to corrode itself. Thank you.
Okay, ma. Any questions regarding this chemical corrosion? No questions? Okay, I have one question.
Sir. Yes, sir.
Can you give me an example for metal which can you give me an example for oxidation of metals, corrosion by excessive oxygen in that aspect, you said that there are according to filling bedwork rule, the porous layer is the oxide layer is porous, non-porous, and volatile, right? According to filling bedwork rule, you can oxide layer into porous and non-porous layers. So can you give me examples for
Yes, sir.
metals forming porous layer and non-porous layer metal oxides?
Sorry, sir. I don't know.
Do you get my question?
Yes, sir.
Do you have any examples which metals form a porous metal oxide layer and which metals do not form or which metals form a non-porous oxide layer?
Porous oxide layers are alkali and alkaline earth metals.
Mm-hmm. Non-porous?
Non. Sorry, sir. Aluminum, tin, lead,
మీకు ఈ క్విజ్ ఎగ్జామ్ లో అడుగుతారు. What to look into it? For example, aluminum forms a non-porous oxide layer.
Yes, sir.
So that the aluminum oxide is a stable oxide layer, therefore it prevents further corrosion.
Yes, sir.
Porous iron forms a porous oxide layer. That's why when you keep an iron rod in the atmosphere, it gets corroded completely during the course of time.
Yes, sir.
Okay, you need to look into different kinds of examples which will form porous oxide layers and non-porous oxide layers. Okay.
Yes, sir.
Okay.
Thank you, sir.
Very good presentation. Next.
Next, number 13, sir. Ram Sai Devi.
Number 13.
Ram Sai.
Okay.
Okay, sir. Next,
Sir,
Maulik,
can you see my screen?
roll number 27.
Sir,
He is sharing something, right? Ramsa is sharing something.
Yes, sir. He did not respond.
sir, am I audible?
Yes.
Good morning, sir. Good morning, my dear friends.
Good morning.
Today, my topic is on synthesis and properties of Buona-S and Buona-N. Let us see our properties and uses of Buona-S. Let us discuss about what is Buona. Bu means butadiene and Na for sodium. Nitrem in several languages including Latin, German and Dutch. And S for styrene.
Very.
Properties of Buona-S. There are several properties like tensile strength, elongation at tear, only viscosity, glass transformation, and polydispersity. And let us discuss about what is Buona-S. The monomers are 1,3 butadiene and styrene. It is formed by the polymerization of 1,3 butadiene and styrene in the ratio of 3:1 in the presence of sodium. And Buona-S is an example of copolymers. It is also called as styrene butadiene rubber. It has significantly less resistance to friction than natural rubber. It is used for making automobiles, tires, and rubber soles. Its commercial name is SBR. And let us see what is the structure of butadiene and styrene. And this is the structure of butadiene, and this is the structure of styrene. Butadiene and styrene undergoes copolymerization to form Buona-S. Properties of Buona-N. Let us see what is Buona-N first, and let us discuss afterwards. And Buona-N is an elastomer, and I have forgotten that to say that Buona-S is also an elastomer. Bionine is known as nitrile rubber. It is a copolymerization. It forms due to the copolymerization of acrylonitrile and 1,3 butadiene. The structure of Biona N. How it forms, let us see. Due to the copolymerization of 1,3 butadiene and acrylonitrile. This is the structure of 1,3 butadiene as we discussed later previous, and this is the structure of acrylonitrile. The copolymerization of 1,3 butadiene and acrylonitrile to form Biona N. The difference between Biona N and Biona S. Both Biona N and Biona S are polymers. Biona N is used for making oil steels and manufacturing of tanks, linking protective gloves, and Biona S is used for making automobiles tires, rubber soles, belts, horses, houses, etc. In order to compare two, these are the basic factors. And what are the uses between Biona S and Biona N? Biona S is used for making automobiles tires, rubber soles, belts, houses, as we discussed later. Previously we discussed. And to compare the two, these are the basic factors. And thank you, sir.
Okay.
సార్ డౌట్ ఉంది అడగొచ్చా సార్?
Yes, yes.
సో బ్యూనాయస్ బ్యూనయన్ లో ఏ కాంపౌండ్ క్యాటలిసిస్ రియాక్షన్ పార్టిసిపేట్ చేసేది సార్? హలో
Yeah, Ram Sai.
Hello, yeah. Once repeat the question.
Bunias and bunion, which of these compound undergoes a catalysis reaction? హలో హలో క్వశ్చన్ అర్థమైందండి?
అర్థమైంది.
చెప్పు.
Amsa, క్వశ్చన్ కి ఆన్సర్ ఏంటి? బియోనాయన్ లో ఏది కెటాలిసిస్ రియాక్షన్ లో పార్టిసిపేట్ చేస్తుంది అని అంటున్నాడు.
Yes sir. Wait a minute. Sorry sir, I unable to tell the question.
Bunion sir. హలో
బియోనాయన్ కెటాలిసిస్ రియాక్షన్ లో పార్టిసిపేట్ చేస్తుంది.
అవును సార్, అక్కడ మనం బ్యూనయన్ లో పెరాక్సైడ్ క్యాటలిస్ట్ వాడతాం కదా సార్.
ఓకే.
బ్యూనయన్ లో మనం సోడియం కత్తలు వాడేది క్యాటలిస్ట్.
ఆయన చెప్పండి, క్రాంతి చెప్పండి, మీరు చెప్పండి
సార్. అది బ్యూనైన్ ప్రిపరేషన్ లో మనం 1,3 బ్యూటాడైన్ యాక్రోనైట్రైల్ వాడతాం కదా సార్.
అవును.
దాంతో పాటు ఇన్ ద ప్రెసెన్స్ ఆఫ్ పెరాక్సైడ్ క్యాటలిస్ట్ వాడతాం కదా సార్. పెరాక్సైడ్ క్యాటలిస్ట్ ప్రెసెన్స్ లోనే ఆ రియాక్షన్ జరిగింది కదా సార్.
రెండు కూడా సోడియం హైడ్రాక్సైడ్ ఆర్ సోడియం మెటల్ ప్రెజెన్స్ లో కూడా రియాక్షన్ జరుగుతుంది. అదే కదా ఫస్ట్ మనం వాటి చెప్పిన స్టేట్మెంట్ లోనే బ్యూనా అంటే బియు అంటే బియు స్టాండ్స్ ఫర్ బ్యూటాడైన్, ఎంయు స్టాండ్స్ ఫర్ సోడియం, ఎస్ ఫర్ స్టైరిన్ అండ్ ఎన్ ఫర్ అక్రైలోనైట్రైల్. ఇందులో కూడా సోడియం ఆర్ పెరాక్సైడ్ ఏదైనా యూజ్ చేయొచ్చు ఇనిషియేటర్ కింద కోపోలిమరైజేషన్ జరగడానికి. Okay, so we'll go to the next presentation.
Mauli sir, number 27.
చెప్పండి కర్నూలు మౌళి గారు.
పోయింది సార్. Sir, is it visible, sir?
Yes, visible.
Good morning, sir. My name is Elmoli Sababu from CSE C section. My topic is working and construction of photovoltaic cell or solar cell. Working of photovoltaic cell. Solar photovoltaic cell are used to convert solar energy to electrical energy.
Mauli.
Yes.
Can you expand your screen or can you rotate your screen so that we can see it very clearly? చాలా మ్యాటర్ పెట్టావు కదా, అది కనిపించట్లేదు మాకు, చిన్న చిన్న అక్షరాల కింద కనబడుతున్నాయి. నువ్వు రొటేట్ చేసి చూపిస్తే లేదా ఫుల్ స్క్రీన్ మోడ్ లో పెడితే.
No, sir.
Yes.
Okay, sir. Energy to real energy. Which are used all solar cells. These are also solar battery or photoelectric cell has been developed by making use of thin water of extra pure silicon, not more than 1 ppm impurity. Means photovoltaic cell means function is to convert solar energy to electrical. Solars are made up of a thin water semi that is light sensitive PN junction photodiode. A PN junction can be simply formed by joining a p-type semiconductor with n-type. As the region of separation is termed as the junction. The p-type region, which is connected to the positive terminal of battery, which contain holes, while the n-type region, which is connected to negative terminal of battery, contain excess of electrons. The holes are repelled by positive charge of the battery, while the electrons are repelled by the negative charge of the battery. Thus electrons and holes are punished towards the junction, thereby which decreases the distance of separation. It means it formation of depletion region due to the imbalance of charges created by diffusion of electrons. Across the junction, there is a potential developed and the current flows through the diode. When the sunlight strikes the top of the n-type semiconductor of 0.2 to 0.5% of sun energy strikes the n-type semiconductor wafer or front contact of solar cell, electrons are knocked out from the material. The electrons travel from n-type to p-type semiconductor, thereby completing the whole electronic circuit or electricity, which is shown by glowing of a bulb attached. Now this is the diagram, sir. N-type and p-type. The sunlight is falling on n-type and the electrons are moving towards p-type junction. Means n-type is doped with some n-type conductors like arsenic, phosphorus, and p-type is doped with the boron or aluminum, etc. Each solar is very small, and series combination of many such solar cells gives rise to photovoltaic module or solar battery. So can be converted directly into electrical energy by photovoltaic cells. A solar cell is transparent wafer containing a semiconductor material with a thickness ranging from less than that of human hair to that of a sheet of paper. Sunlight energizes and causes electrons in a semiconductor to flow, creating an electric circuit. Meanwhile, to electricity stored and bulb diagram. Solar system contains so many parts: solar array, a blocking diode, battery storage, load, power condition, switch
Your
and
voice
circuit
is
breaker.
breaking. Your voice is breaking.
One. No, sir. Solar photovoltaic system. They contain many parts: solar array, a blocking diode, battery storage, conditions and circuit breaks. And the material example junctions, homojunction. If N and P type semiconductors are derived from same element, it's called homojunction. Example silicon with N and P heterojunction. If p-n junction is formed from two different semiconductor materials, it is called heterojunction. Example Cu2s and cadmium sulfide and copper sulfide. Schottky junction. Depositing a thin layer of a metallic conductor like platinum on a PRN type semiconductor. Schottky junction photovoltaic cells made with amorphous silicon are more efficient and cheaper. Metal insulator semiconductor. In this, a very thin layer of insulator is the semiconductor. Semiconductor in a very thin layer of insulator is deposited in between the two semiconductors. Example, tin oxide in between silicon. Liquid interface solar cells. These are formed using top surface of a liquid type. Solar energy application. Like example. Liquid plate collector for a water heating by solar energy, and solar cooker, solar furnace, solar power plant, and the solar cell and solar panels. Materials used in solar cells are silicon. Over 95% of cells in commercial production are silicon p-n junction, while consumer items are now using amorphous silicon p-n cells. Band gap is 1.1 electron volt. Experiments have demonstrated that silicon cell could convert about 15% of the terrestrial sunlight into electricity. And silicon cells of types NR type structure are used in gallium arsenide, cadmium sulfide, and cadmium cyanide, etc. Thank you.
So, any questions regarding this solar cells?
Doubt, sir.
Yeah, please.
Sir, solar plate ఉంటుంది. దాంట్లో సోలార్ సెల్స్ అన్ని సిరీస్ లో కనెక్ట్ చేస్తారా, ప్యారల్ కనెక్ట్ చేస్తారా సార్?
చెప్పండి.
సిరీస్ సార్,
మీరు చెప్పండి.
సిరీస్ సార్, పవన్ సిరీస్.
ఓకే, థ్యాంక్ యూ మోలీ సార్. రైట్ సార్,
అంతేనా? ఓకే, నాకు ఒక డౌట్ ఉందండి.
చెప్పండి సార్.
ఈ సోలార్ సెల్ లో పిఎన్ జంక్షన్ డయోడ్ జనరేట్ చేస్తారు కదా. సో పి టైప్ సెమీ కండక్టర్, ఎన్ టైప్ సెమీ కండక్టర్ ని కనెక్ట్ చేస్తారు. సో ఈ సన్లైట్ వచ్చి పి టైప్ సెమీ కండక్టర్ మీద పడేలా అరేంజ్ చేస్తారా, ఎన్ టైప్ సెమీ కండక్టర్ మీద వచ్చి పడేలా అరేంజ్ చేస్తారా?
ఎన్ టైప్ సార్.
ఎందుకు
అంటే అక్కడ ఉన్న ఎలక్ట్రాన్స్ అనేవి కింద పీ టైప్ లో ఉన్న హోల్స్ కి రావాలి కదా సార్. అప్పుడు డిప్లేషన్ ఫామ్ అయ్యి ఎలక్ట్రిసిటీ కనెక్ట్ అయితే అప్పుడు బల్బు అదే కరెంట్ జనరేట్ అయ్యి బల్బు వెలుగుతుంది కదా సార్.
ఓకే, అందుకని ఎన్ టైప్ సెమీ కండక్టర్ పైన ఉంటుంది, పి టైప్ సెమీ కండక్టర్.
అవును సార్.
ఓకే ఓకే, థ్యాంక్ యూ.
ఓకే, థ్యాంక్ యూ సార్.
ఇంకా ఏమైనా డౌట్స్ ఉన్నాయా? మీరందరూ ఏం మాట్లాడలేదు. రేపు సెకండ్ మిడ్ లో కనుక మార్కులు ఎవరికైనా సరిగ్గా రాలేదా చెప్తాను. ఏ క్వశ్చన్లు అడగట్లేదు అంటే మీరు వినకపోయినా అయి ఉండాలి, మీకు బాగా అర్థమైనా అయినట్టు ఉండాలి. వినకపోతే ప్రాబ్లం లేదు, విన్నారనే ఫీల్ అవుతున్నాను. నేను నెగిటివ్ సెన్స్ లో తీసుకోను కాబట్టి పాజిటివ్ సెన్స్ లో తీసుకుంటున్నాను. అందరూ బాగా వింటున్నారని. ఓకే, నెక్స్ట్ ప్రెజెంటేషన్
నంబర్ 30 సార్, వినయ్.
వినయ్, నంబర్ 30.
Sir, is my screen visible?
Yes.
Okay, sir.
Perfect.
Today my topic is refractory. Definition of refractory: refractories are inorganic, metallic, and non-metallic oxides withstand to high temperature without deformation. It's called refractories. As we see in the preparation of porcelain shipment, is the eating zones. The 3 eating zones are surrounded by the rotary clean is surrounded by a refractory. So the materials which are useful at high temperatures are refractories. Examples: Al2O3, Cr2O3, SiO2, etc. Characteristics of refractories: they should be chemically inert, they exhibit high mechanical strength, exhibit high abrasion resistance, as least possible expansion and contraction. Types of refractories: based on the chemical composition or nature, they are classified into 3 types: acidic refractory, basic refractory, neutral refractory. Acidic refractories. Acidic refractories consist of mostly acidic materials and they are used in only in acidic environment. Example: fire clay, SiO2, etc. Basic refractories. Basic refractory consists of mostly basic materials and they are used in basic environment. Example: manganese oxide, dolomites, etc. Neutral refractories. They consist of neutral natural raw materials and used in both acidic and basic environment. Example: graphite, zirconia, SiC, etc. Based on the fusion temperature, refractories are classified into 3 types: low refractories, high refractories, super refractories. Low refractories at the temperature of 1600 degrees centigrade to 1800 degrees centigrade. Example: fire clay. High refractories at the temperature of 1800 degrees centigrade to 2000 degrees centigrade. Example: chromites and silica. Super refractories at the temperature greater than 2000 degrees centigrade. Example: zirconia. And the properties of refractories. First, refractness. Ability of a material to withstand the heat without appreciable deformation at operating temperature is called refractness. It can be determined by finding fusion temperature of the refractory material. Fusion temperature can be determined by pyrometric cone equivalent test. The temperature at which the refractory deform under its own weight is known as fusion temperature. These cones are in pyramidal and have a height of 38 millimeters of a triangle base and 19 millimeters long sides. They allow to heat under 10 degree per minute as the result undergo fusion at a different temperature. This temperature at which the fusion or softening of a test comes occur is shown by the apex touching the base. So the temperature at which the apex touching the surface is the fusion temperature. By that we find the refractness of the refractory material. Refractness under load or strength. It gives mechanical strength of the refractory. It is ability of a material to withstand to underload without appreciable deformation at operating temperature. Refractors underload test is performed by heating a refractory specimen of a size 5 cm square and 75 cm height under constant load 3.5 to 1.75 kg per centimeter square, and it can be found by plotting the graph between deformation height of the refractory and the temperature. Next, dimensional stability. Resist to any volume change at operating condition is called dimensional stability. Permanent expansion. When one crystalline form of a refractory is transformed into another crystalline form of low density is the dimensional stability. Example: quartz to dynamite to cristobalite. The specific gravity of the quartz is 2.65 and cristobalite is 2.32. So the decreasing of the low density, it occurs permanent expansion. Next, permanent contraction. When one crystalline form of a refractory is transformed into another crystalline form of high density, it is called permanent contraction. Example: amorphous manganese oxide to periclase. The specific gravity is 3.05 and periclase specific gravity is 3.54. So the increasing of the specific gravity, the permanent contraction takes place. Next, porosity. Porosity is the ratio of its porous volume to bulk volume, as P is equals to W minus D by W minus A into 100. W stands for weight of the saturated specimen, D stands for weight of the dry specimen, A stands for weight of the saturated crystal submerged in water. And it is a very important property of the refractory bricks because it affects many other characteristics like chemical stability, strength, abrasion resistance, etc. So by a good refractory generally has a low porosity. Thermal spalling, the breaking, cracking, peeling off or fracturing of a refractory brick or a block under high temperature is called thermal spalling. So good refractory must show a good resistance to thermal spalling. And thermal spalling occurs due to the sudden variation of temperature in furnaces, which causes uneven expansion and contraction. These are properties of the refractories. Thank you. Sir, completed, sir. Hello?
Any questions? So if there are no questions, we'll move to the next presentation.
Number 32, Ashish.
So yes, sir. 1 minute. Sir, is my screen visible?
Yes, yes.
Good morning, everyone. I'm Ashish, and my presentation is about setting and hardening of Portland cement and decay of concrete. Firstly, we shall discuss about setting and hardening of Portland cement. We know that by the manufacturing of Portland cement, the main chemical constituents of Portland cement are dicalcium sulfate, tricalcium sulfate, tricalcium aluminate, and tricalcium aluminoferrate. And when the cement is mixed with water to form a plastic mass, it's called cement paste. And the hydration reactions begin then, resulting in the formation of gel and crystalline products. The interlocking of the crystals finally bind the inert particles of the aggregates into a compact rock-like material. The process of solidification comprises mainly of two steps, namely setting and hardening. Firstly, we shall discuss about setting. Setting is defined as the stiffening of original plastic mass due to the gel formation. And it is due to the hydration of tricalcium aluminate and it's due to the hydration of tricalcium aluminate and the gel formation of tetracalcium aluminoferrate. And during this, the chemical constituents of the Portland cement reacts with water and becomes hydrated. So along with the formation of metastable gels, we get some crystalline hydration products. So when the constituents are reacted with water, some energy will be released, namely the enthalpy of hydration or heat of hydration of cement. We should take care that the structure formed should release the heat of hydration efficiently, or it results in the cracks of cement, which deteriorates the structure later. So this heat of hydration varies from reaction to reaction, ranging from 250 kilojoules per kg to 880 kilojoules per kilogram. And this initial setting of the cement should not be more than 45 minutes for an ideal cement. And it can be tested with a standard needle by piercing it into cement. And we may always wonder and think about what is the use of gypsum in cement. Tricalcium aluminate combines with water very rapidly with the evolution of large amount of heat. After the initial set, Now, the paste becomes somewhat stiff. However, the added gypsum retards the dissolution of C3A by forming insoluble calcium sulfoaluminate. The reaction prevents high concentrations of alumina in the cement solution, thereby retarding the early initial set of cement. So here, gypsum acts as a retarder and increases the time for initial setting of cement, thereby increasing the efficiency. And next, the second process that happens for the increasing the strengthening of cement is hardening. And it is due to the formation of tobermory gels by dicalcium silicate and tricalcium silicate, plus the crystallization of calcium hydroxide and hydrated tricalcium aluminate. Here, this process may take long, as the tobermory gels takes at around 28 days after the gelation of di and tricalcium silicates. And during this process, we always follow a process named curing. Curing is a process which facilitates the hydration reactions of cement constituents to enable the cement develop the desired properties of sufficient extent. As to meet the requirements, curing is usually prepared and performed by maintaining the required moisture content and a favorable temperature in the concrete. During and after its placement, in order to provide ideal condition for the quicker and completion of hydration of cement constituents and development of desired products, we follow curing. And we should keep in mind that while curing, we should use the water without any hardness, because if hardness, if any, is there, then the cement may deteriorate later. And now going about and discussing about deterioration of concrete. Firstly, we shall discuss about what is concrete. Concrete is a building and structural material obtained by mixing a binding material, inert aggregate, and water in suitable proportions, and which can be readily used or molded into desired shape. It's compact, rigid, strong, and durable. High quality concrete is very much durable without any need for protective coatings. However, concrete is susceptible to several agents, causing expansion and cracking. Cement concrete is mechanically very strong, but is very susceptible to chemical attacks. And some of these attacks include acid attack. Concrete contains free calcium hydroxide. So in acidic water, lime dissolves, making the concrete weak. So as the pH value decreases, the deterioration of concrete increases. So, so to prevent this, acid-proof polymer-modified concrete must be used to resist this acid attack. Second type of attack, sulfate attack. Sulfates are present in soil, groundwaters, and marine waters environments. Sulfates react with tricalcium aluminate to give bulky aggregates, causing cracks due to expansion. This is avoided by using sulfate-resistant cements, which contains less amount of tricalcium aluminate. Such danger is avoided by eliminating tricalcium aluminate from cement composition but replacing it with tetracalcium aluminoferrate. Third type of attack, magnesium salts attack. Magnesium salts are present in groundwater and marine environment, react with calcium hydroxide to give magnesium hydroxide, which does not have binding properties. Magnesium salts destroy tricalcium sulfate silicate and dicalcium silicate and tricalcium aluminate. And carbon dioxide. And the fourth type of attack is due to carbon dioxide. Diffusion of carbon dioxide into concrete and conversion of calcium hydroxide to calcium carbonate is called carbonation. And this carbonation into a specific concrete structure depends on the porosity of the concrete. Good quality concrete is less porous and the diffusion would be less. And in the absence of the, due to the carbonation, the cement lacks hydroxide, calcium hydroxides. So in the absence of hydroxides, iron oxide coating becomes porous and non-protective. And this leads to the deterioration of concrete. The fifth type of attack is chloride attack. Chlorides enter the concrete through water used for construction and diffusion from the environment. Chlorides diffuse through porous and low quality concrete and reach the reinforcement. In presence of chlorides, the protective oxide layer around iron becomes less protective and porous. That causes electrochemical corrosion of iron. So this is why we should take care that not to use hard water during curing of cement. So for protecting the concrete, we must follow some certain measures by giving a coating of bituminous material. So in these processes for protection of concrete, our main aim is to reduce the contact between concrete and air. So for this, we use the process of adding bituminous materials on concrete. This prevents direct contact between concrete and water, and by coating the surface with silicon fluoride in soluble form together with oxides of zinc, magnesium, and aluminium, the precipitate of calcium fluoride so formed in the capillaries prevents dissolution of lime and thereby protects the concrete structure. And thank you. But finally, we have a common myth that after the hardening of the cement attains its complete strength and it can't be developed any further. But the truth is, the cement always hardens and it would develop its strength forever. But its main strength, which is almost 99%, will be attained during the first 2 weeks after the process of gelation of dicalcium and tricalcium silicates. After that, its development of strength will be decreased exponentially. Thank you.
So any questions? Very nice presentation, Ashish.
Thank you, sir.
The thing is, you may ask any questions to the listeners if you want.
Sir, okay, sir.
మొన్న ఎవరో చెప్పారు ఆల్రెడీ ఈ సెట్టింగ్ అండ్ హార్డనింగ్ ఎవరు చెప్పారు?
Sir, can I ask it out to listeners?
Yes, of course.
Sir, what type of reaction happens during the acid attack on concretes?
Anyone from the listeners?
Neutralization.
Yes, sir, that's right.
Very good. ఎవరో చెయ్యి పైకెత్తారు. So any questions, or can I conclude this session, this presentation? Can I move for the next presentation? Sairama.
Yes, sir.
Okay, Muni, go for the next presentation.
Next, number 38, Ivagopi.
Good morning, sir. Good morning, sir.
Good morning. Welcome.
Is my voice audible, sir?
Yes, your voice is audible and your presentation is visible.
Yes, sir. My name is Yogopi Anjani Kumar. I am from CSCC. Today I am going to give a brief explanation which was related to the polymers.
We need a detailed explanation. We don't want a brief explanation. We're expecting a detailed explanation from your side.
Yes, sir. I'm going to give a brief I am going to give a complete explanation on synthesis of polythene, properties of polythene and uses of polythene, and also synthesis of polyvinyl chloride, properties and its uses. Let us begin with synthesis of polythene. Synthesis of a polymer is nothing but polymerization of the polymer. Polymerization is the process of formation of the polymers from its starting materials that are monomers. Polythene is an additional polymer. Addition polymers is a polymer which undergoes addition polymerization where the molecules of same monomer or different monomers add together to form a polymer. Polythene is mostly used as thermosetting polymer in many industries. Polythene is classified into two types based on their densities. They are low density polythene and high density polythene. Low density polythene. When the monomer ethane is polymerized with the help of chain initiator. Usually the chain initiator is an active molecule which attacks the monomer to initiate the chain formation. This further goes chain propagation, that the chain initiated chain then attacks more monomer molecules and then chain termination. Here the chain initiator or catalyst is benzoyl peroxide in presence of oxygen at 1000 to 2000 atmospheric pressure, and the formation of low density polythene follows as reaction there. Properties and uses of low density polythene. Low density polythene has melting point around 110 degrees to 125 degrees centigrade, and it is 40% crystalline, that is, it is soft and waxy solid. Its density is around 0.91 to 0.92 grams per milliliters. It is insoluble in any solvents at room temperature. And its uses is, it is used for films, tableclothing, packing materials, squeeze bottles, pipes, etc. Then high density polythene. And the monomer ethane is polymerized with the help of chain initiator, Ziegler Netta catalyst, which is a mixture of triethyl aluminum and titanium tetrachloride at 6 to 7 atmospheric pressure. Then high density polythene is formed as the reaction follows. And its properties are, its melting point is around 144 to 150 degrees centigrade, and it is 90% crystalline, so it is rigid. Its density is 0.965 grams per milliliters, and it was chemically more resistant than low density polythene, and it is used for films, detergent bottles, pipes, industrial clothing and filters, etc. Let us discuss the synthesis of polyvinyl chloride, which is also known as PVC. Generally, polyvinyl chloride is an addition polymer of the vinyl chloride, whereas vinyl chloride is chloroethylene or chloroacetylene. It is prepared by treating the acetylene with hydrochloric acid at 60 to 80 degrees centigrade at 1 to 1.5 atmospheric pressure. PVC is obtained when water emulsion of vinyl chloride is heated in presence of chain initiator, that is catalyst, benzoyl peroxide or hydrogen peroxide, and its reaction as follows. Properties and uses of polyvinyl chloride. PVC is insoluble in alcohol, water, and hydrocarbons. As it is insoluble in water, it can also useful to prepare some materials which are waterproof, and it is insoluble and it is soluble in chlorinated hydrocarbons and ketones. It is colorless, odorless, non-flammable, and chemically inert substance. It has resistance to light and atmospheric oxygen too. And its uses, it is used for production of cable insulation equipment parts, pipes, laminated materials, and in fiber manufacturing. That's it. Thank you.
Thank you. Thank you, Yogopi. So any questions from audience side? Or any questions from your side to audience?
Why do we use peroxides as chain initiator for addition polymerization?
Who asked this question, Yogopi? You or someone?
Yes, sir.
Yeah. Anyone from audience side? Can you answer? Why do we use peroxides in addition polymerization? ఎవరైనా చెప్తారా ఎందుకు పెరాక్సైడ్స్ యూజ్ చేస్తాము అడిషన్ పాలిమరైజేషన్ లో?
ఫ్రీ రాడికల్ పాలిమరైజేషన్ జరగటానికి.
Yes, sir.
To create free radicals, they are initiators.
Yes.
Very good. So can I move to the next presentation, or you have any questions, Yogopi?
Next presentation.
Okay. Muni?
Raju 62, sir. Sir, good morning, sir.
Yeah, good morning. Share your screen.
Okay, sir. సార్ కనిపిస్తుందా సార్?
కనిపిస్తుంది కానీ నువ్వేంటి డాక్యుమెంట్ తీస్తావు డైరెక్ట్?
సార్ అది పీడిఎఫ్ రాసిన సార్, అది పీడిఎఫ్ కాలే, అందుకని ఓపెన్ చేసిన సార్.
ఓకే ఓకే, అది రొటేట్ చేసి పెట్టు కొంచెం. సరే చెప్పలేరా మరలా?
Hello friends, my topic is galvanizing process. As we guys know, galvanization is applying thick layer of zinc on the surface of a metal in order to act as shield against external environment, actually to prevent from corrosion. Okay, let us briefly understand about galvanizing. Galvanizing is an anodic coating process, which is coating the more active metal by dipping in a less active metal which is in molten state. More active metal must be have higher melting point, because when we dip the metal in the molten zinc, it should not be melted. There are many steps involved in this process. The first step is degreasing or caustic solution. Okay, the metal is cleaned here. In order to remove dirt, grease, oil of the metal should be dipped in an alkaline solution. This is degreasing process. And then the metal is dipped in water called rinsing. And later we do pickling process. Pickling means here pickling we do pickling because to remove the oxide layers of the metal which is already present over the metal. And then it is again rinsed. Afterwards we do fluxing. Fluxing of metal should be done after the rinsing. To prevent oxidation of a metal, we do fluxing. Fluxing contains zinc chloride solution and ammonium chloride solution. The combination of both this zinc and ammonium chloride called Zn zinc ammonium chloride flux. These fluxes are called. And then the metal is dried in order to avoid splashes, and it is dipped in the galvanizing bath. Later, the metal should be dipped in galvanizing bath to remove the to add zinc coating to the metal. Here in the galvanizing bath, the zinc and the iron diffuses and form zinc iron alloys. And later it is quenched so as to harden the topmost layer of the metal, and and finally it is cooled. After these steps, the thick layer of the zinc is coated strongly over the base metal. These this is galvanizing process, and let we know about the uses of the galvanizing process. Galvanizing process. Galvanizing materials are used in steel wires, pipes, nails, screws, nuts, and bolts, and then stream frames and the rooftops for construction. There is a note in galvanized materials. It should not be the galvanized materials must not be used to store acidic foodstuff, because zinc is more active metal, so it dissolves with the acidic foodstuff and poisons the foodstuff. This is about galvanizing. Thank you, sir.
Thank you. Thank you for your presentation. Any questions? From either side. Raj, you may ask any question. అడగాలనుకుంటే అడగచ్చు, లేదా లేకపోయినా ప్రాబ్లం లేదు. నీకు ఎవరి మీద కోపం ఉంటే వాళ్ళ పేరు చెప్పి మీరే అడగచ్చు.
అట్లేం కోపాలు లేవు సార్.
ఈ సిఆర్ ఏం మాట్లాడట్లేదు, ఓన్లీ ఆర్గనైజ్ చేస్తున్నారు తప్ప. ఆయన అడుగు క్వశ్చన్.
సిఆర్, హలో. ఎస్ సార్. సిఆర్ ఒక క్వశ్చన్ అడిగానా?
క్వశ్చన్ అడుగు. ఇక్కడ పరిచయాలను పలకరింపులు అక్కర్లేదు.
సిఆర్ డౌట్ ఉంటే అడుగురా.
ఓకే ఓకే ఓకే. నెక్స్ట్ ప్రెజెంటేషన్.
థ్యాంక్ యూ సార్.
44 సతీష్ సార్.
ముని నువ్వేం అడగట్లేదు, నిజంగానే ఏం మాట్లాడట్లేదు. అన్ని వింటున్నావా
సార్?
అన్ని వింటున్నావా ప్రెజెంటేషన్స్ అంటున్నాను.
ఎస్ సార్.
Sir, is my screen audible, sir?
Your screen is visible and you are audible. No problem. Continue.
Good afternoon, sir, and good afternoon, my dear friends. Now I would like to discuss about fiber reinforced plastics. Fiber reinforced plastics are also called as fiber reinforced polymers. It is nothing but a composite material made up of polymer matrix reinforced with fibers, and the polymer usually is an epoxy, vinyl ester or polyester thermosetting plastic, and the fibers are usually glass, carbon or aramid, and rarely we use paper, wood and asbestos as fibers. The development of fiber reinforced plastic was researched in the 1930s, and the first fiber reinforced plastic is bakelite. Fiber reinforced plastics are commonly used in aerospace, automotive, marine and construction industries. Let us see applications of fiber reinforced plastics. And this picture is glass aramid hybrid fabric. It is used in case of high tension and compression. These fiber reinforced plastics are best suited for any design program that demands weight savings, precision engineering, definite tolerances, and simplification of parts in both production and operation. A molded polymer product is cheaper, faster, and easier to manufacture than other polymers. In fiber reinforced plastic, I would like to explain about glass fiber reinforced plastics and carbon reinforced plastics. Let us see the introduction of glass fiber reinforced plastics. It is a sustainable material challenging the traditional market. Today's life without this glass fiber reinforced plastic would be difficult. These glass fiber reinforced plastics are discovered for industrial purpose in the beginning of 20th century. Let us see how these glass fiber reinforced plastics are made up of. It is a composite material that consists of polymer matrix and glass fibers. And the polymer matrix we usually use epoxy, vinyl ester or polyester thermosetting resin. And these resins bring environmental and chemical resistance to the product. And the glass fibers add strength to the composite. Here the reinforcing material is glass fiber. The most common type of glass fiber used for GRP is E-glass, which is aluminum borosilicate glass. And next, why glass fiber reinforced plastics are so strong? As compared to many other materials, these resins, polymer matrix resins and glass fibers complement each other to form stronger compounds. These resins are strong in compressive loading, and the glass fibers are very strong in tension. So these glass fiber reinforced plastic becomes a material that resists both compressive and tensile forces very well. And let us see the characteristic properties of glass fiber reinforced plastics. They have these features many beneficial characteristics. It comes with, they have very low weight at high mechanical strength and resistance against chemicals and corrosion, and UV radiation and temperature stability and environmental friendliness. These are some of the characteristic properties. And let us see the applications. These applications include aircrafts, boats, automobiles, bathtubs, and swimming pools, etc. Here are some of the examples shown below: aircrafts, boats, and swimming pool. And let us see about carbon fiber reinforced plastics. These carbon fibers were developed in the mid 1960s. It is the composite properties are mainly influenced by choice of fibers. This CFRP is a lightweight, high strength composite material. Let us see what it is made up of. It is a composite material made up of polymer matrix and carbon fiber. Carbon fiber, 90% of carbon fibers are produced from tan polyacrylonitrile. And the polymer matrix we use is usually epoxy. And one of the method of producing these carbon fiber reinforced parts is by layering the sheets of carbon fiber cloth into a mold in the shape of final product. Here cloth fiber is used to optimize strength and stiffness properties of resulting material. Then the mold is filled with epoxy and heated to get the final product. Let us see some of the properties of carbon fibers. They have excellent tensile properties, low densities, high thermal and chemical stabilities in the absence of oxidizing agents, and they also have good thermal and electrical conductivities and excellent creep resistance. And let us some of the advantages. There are mainly 4 advantages. First one is strength. These carbon materials are very tough and strong. And the second one is weight. Despite its strength, carbon fibers are actually very light in weight. And the third one is stress resistance. The parts made from carbon fiber are less prone to wear and tear. And the fourth one is corrosion resistance. Carbon fiber is durable in corrosive environment too. Let us see the applications of carbon fiber. These are used in sporting equipments, automotive parts, aerospace engineering, civil engineering, medical applications, and environmental applications, and also things at home. Here are some of the examples we can see. The difference between fiber reinforced plastics and glass fiber reinforced plastics. They differ in properties. Carbon fiber reinforced plastics have lightweight and low densities, whereas glass fiber reinforced plastics have medium weight and medium density. And they also differ in reinforcing material. In CFRP, the reinforced material is glass fiber, and in GFRP, the reinforced material is glass fiber. Conductivity, the plastic are very conductive, and whereas glass fiber reinforced plastics are insulative, and the cost of carbon fiber reinforced plastics is very high when compared to glass fiber reinforced plastics, as these are very less expensive. Thank you.
Thank you. Any questions?
Sir,
Yeah.
what is meant by creep resistance of carbon fibers?
Satish. Answer this question.
Sir, can you repeat the question?
What is meant by creep resistance of carbon fibers? What is meant by creep resistance? That's it.
Sir, I don't know, sir.
మీకు తెలుసా?
Sir? Tendency of a material to slowly deform over a long period of exposure to high levels of stress. Is it correct, sir?
Yes, yes.
Thank you, sir.
Okay. So ఇంకా ఎన్ని ప్రెజెంటేషన్స్ ఉన్నాయి ముని?
సార్ ఇంకా 5 to 6 ఉన్నాయి సార్.
కంటిన్యూ చేసేద్దామా?
ఒక 3 చెప్దాం సార్.
ఓకే.
ఒక 3 చేద్దాం సార్.
ఓకే ఓకే. నెక్స్ట్
46 పృథ్వీ.
కొంచెం స్పీడ్ అప్ చేయండి ప్రెజెంటేషన్స్. క్రిస్ప్ గా ప్రెజెంట్ చేయండి. నెక్స్ట్ 46 పృథ్వీయా?
ఎస్ సార్. Good afternoon, everyone. Good afternoon, sir.
Good afternoon.
I am Prithvi Narayana from CSCC, roll number 46. Today, I am going to tell about the synthesis and properties of bunoids and bunoyan. When you come the main polymer, the polymer definition, the term polymer is derived from the Greek. We can say poly means many and mers means units or parts. A polymer may be defined as a long molecule formed by repeated combinations of small and simple chemical compounds which are known as monomers. Whereas polymerization we can redefine as simply we can define as the process by which the monomers are transformed into a polymer is called polymerization. When you come to the types of polymerization, there are two types, basic types of polymerization: addition polymerization, condensation polymerization. Bunoids and bunoyan undergoes addition polymerization. Copolymer we can define as the polymer made by addition polymerization from two different monomers are termed as copolymers. Example, Buenos N. Synthetic rubbers are elastomers. Synthetic rubbers are also called as elastomers. An elastomer is a synthetic rubber which is vulcanized man-made polymer that can be stretched to at least twice in length, but it returns to its original position as soon as stretched force is released. We can say Buenos and Buenos are the synthetic rubbers. When come to the preparation of Buenos, Buenos rubber is a copolymer obtained by the addition of butadiene and styrene at a ratio 3:1. 75% of the butadiene and 25% of styrene in an emulsion system in presence of free radical initiator like benzoyl peroxide with the support of dextrose. We can say we can tell it as like glucose. So according to the temperature, we can divide the produced rubber into two types. One is cold rubber. Cold rubber, the polymerization carried at the temperature minus 15 degrees Celsius to 5 degrees Celsius. When you come in this cold rubber, at this temperature, the chain length can be controlled. If the temperature is 50 degrees Celsius, then the rubber is called a hot rubber. And in this case, the chain reaction cannot be controlled. This type of synthetic rubbers are more efficient than natural rubbers. Here, when we come to the properties of BNIS, it is high abrasion resistance. It means the abrasion means the process of scrapping or we can say the process of scrapping. High loading bearing capacity and resilience. It is it get oxidized in the presence of ozone. It swells in oils and solvents, and it needs more accelerators for vacuumization. It can be vandalized by the sulfur, but quality required is less. And when we go to the uses of the BNS, it is usually valued in battery ties in shoe heels and soles, gas sticks, and even chewing gums. We can use the natural rubbers and synthetic is a same, a little bit same, but synthetic rubbers are more efficient when compared to the natural rubbers. It is extremely used in coated papers, being one of the most cost efficient to resin to bind the pigments coating. And another use, it is also used in the building applications as a sealing and binding agents behind the renders as an alternative to PVA. PVA means polyvinyl alcohol. And another uses is additionally it is used in some rubber cutting boards. When it comes to the preparation of BNS, we can call it as a nitrile rubber or a NBR. Butadiene rubber is a copolymer obtained by the addition of butadiene and acrylonitrile at the ratio 3:1 in an emulsion system in the presence of free radical initiator like benzoyl peroxide. Synthetic rubbers can be recognized as there is a weak pi bond present in the long backbone polymer chain. As we can see by observing this diagram, we can observe what the process has been done here. Such types of these synthetic fibers are more efficient than natural rubbers. These rubbers have high tensile strength, low abrasion, oxidation, and resistance to the whether oil or basic acid. Due to this presence of CN group, this is less resistance towards base when compared to BNS. When we compare both BNN, we can say because of these CN group, this resistance is very less towards base. When we come to the properties of BNS, nitrile is a family of unsaturated copolymer of two propene, nitrile, and butadiene monomers. Its physical and chemical properties are very depending on the polymer's composition of nitrile. So the majority here we can observe the majority of the composition, the property and chemical and physical properties are depending on the polymer composition of the nitrile. The more nitrile there is within the polymer, the higher its resistance to its oils, but the lower its flexibility. In this point, we can observe when the more nitrile is there in the polymer, the higher its resistance to the oil, but it's low its flexibility. When you come to flexibility, it is very low. And when we come to next property, nitrile rubber is more resistant than natural rubber to the oils and acids, and it is superior strength. So by observing this, by reading this line, we can say that nitrile rubber is more resistant than natural rubber to the oils and acids, and it is superior strength, but it is very strong. But suffers from the inferior flexibility. In flexibility, it may suffer. When community uses of the bunias is used in automotive and aeronautical industries to make the fuel and oil handling hoses, seals, and grommets. It is next point. It is used to make protective glosses in the nuclear industry. And when come to the next point, it is ideal material for the aeronautical applications, as N can be withstand a range of temperature from -42 to 108 degrees Celsius. By observing the previous slides, we can differentiate we can say the differences between the BUNIS and BUNIN. When you come to BUNIN, the monomers we can say 1,3 butadiene and acrylonitrile. Here we can observe the 1,3 butadiene are same, but the another monomer is different between the BUNIN and BUNIS. BUNIN is also called nitrile butadiene rubber, and BUNIS is also called styrene butadiene rubber. When come to the BUNIN, it is formed by a polymerization of 1,3 butadiene and acrylonitrile in the presence of sodium. When come to BUNIS, it is formed by the polymerization of 1,3 butadiene and styrene in the ratio 3:1 in the presence of sodium. When come to the uses, it is very different. It's not the same. BUNIN and BUNIS are the uses are different, and it is very useful polymers when compared to other. It's more efficient, and it is more useful for the users in making oil seals, manufacturing of tanks. We can observe in BUNIS. In BUNIS, these materials are used for the making automobile stuff. Thank you, sir.
Okay, sir. This is the last one. Anusha, 57.
Hello, sir. Hello.
Okay, continue,
My screen is visible, sir.
Yeah, continue.
Hello everyone, this is Anusha from CSC C section. Let's have a brief discussion about refractories and its properties. And definition of refractory. Refractory is a ceramic material that can withstand very high temperature without undergoing any change chemically or physically, like melting and deformation in shape. And they don't lose their strength and their form. And this can be used for constructions of furnaces, kilns, ovens, and converters, etc. And they are produced from the natural and synthetic materials. And let us move on to the characteristics of refractories. It should be infusible at temperature to which it is liable to be exposed, and it must be chemically inert towards the corrosive action of gases, metallic liquid, and slags which are produced in the furnaces. It should resist the abrasion action of flames, molten metal, slags, and flue gases, etc. At operating temperature, it should be able to withstand the overlying load of structure. And refractories should not crack and suffer loss in size at operating temperature. Uniform expansion and contraction should be takes place while temperature rise and fall respectively. And next, classification of refractories. And based on chemical composition, they are mainly classified into three types. They are acidic refractories, basic refractories, and neutral refractories. And the first one is about acidic refractories, in which it consists of acidic materials like alumina, silica, and they are generally not attacked or affected by the acidic materials, but easily affected by the basic materials. And examples of acidic refractories are alumina, silica, and fire clay refractories. And basic refractories, these are used in the areas where slags and atmosphere are basic. And these are refractories which consist of basic materials, AO, MgO, and etc. And these are not attacked by the basic materials, but severely attacked by the acidic materials. Example, magnesite and dolomite refractories. And next, neutral refractories. And they are used in the area where slag and atmosphere are either basic or acidic, and they are chemically stable to both acids and bases. These are made from weakly acidic or weakly basic materials like carbon, chromides, etc. And these are not attacked by either acids or bases. Example, graphite, zirconia, carborundum, and chromides. And we'll go to properties of refractories. Refractoriness. It is the ability of a material to withstand the heat without appreciable deformation of the particular surface conditions. And refractories are mixtures of metallic oxides, so they don't have a sharp fusion temperature. Pyrometric cones test. And the soft temperature of refractory materials are generally determined by using pyro cones test. Softening temperature is much greater than the operating temperature. And next, refractoriness under load. And it is an important consideration because refractor fails at lower temperature when load is applied, and the material must be strong enough to resist the physical wearing away and to take load. In many cases, especially in taller furnaces, the refractory has to support heavy load and strength under the combined effect of temperature, and load is an important criteria. It is also indicated by pyrometric cone equivalence. Dimensional stability. Dimensional stability can be defined as resistance of material to any volume to high temperature over a prolonged time. This dimension can be reversible, it can be irreversible. Irreversible changes may result either in contraction or expansion of the refractory. Examples of dimensional stability are silica bricks and magnesite bricks. And next, thermal expansion. Solid materials on heating expands and cooling it contracts. So in designing of the practical furnaces of a refractory, material should have least possible thermal expansions, as the expansion affects all the dimensions, length, area, volume of the body. And next, thermal spalling. Thermal spalling is breaking, cracking, peeling off, or fracturing of a refractory under higher temperature. So a good refractory show a high resistance to thermal spalling. It is generally in temperature, which can affect uneven expansion contraction within the mass of a refractory of internal stress strain. Next, porosity of refractory contains pores either due to manufacture defects or deliberately. Porosity is the ratio of its pores volume to the bulk volume. And the densest and least porous refractories have highest thermal conductivity. A good refractory should have low porosity. Chemical inertness. A refractory should be chemically inert and doesn't easily form fusible products with slags, furnaces, gases, and abrasion resistance, and it should resist the abrasion action of flue gases, flames, fluxes, and slags. Electric conductivity. Refractories to be used for lining electric furnaces should have low electricity conductivity. Bulk density. This particular property mainly influences many other important properties. Bulk densities will improve strength, dimensional stability, resistance, heat capacity. Thank you.
ఓకే, ఇంకా చాట్లో అటెండెన్స్ పెట్టని వాళ్ళు ఉంటే పెట్టేయండి ఫాస్ట్గా. రెండోసారి పెట్టద్దు.
ముని ఇంకా ఎంతమంది మనకి ఇవ్వాల్సి ఉంటుంది ప్రజెంటేషన్స్? 10
సార్ అంటే ఇంకా రెడీగా అయితే 6 మెంబర్స్ మళ్ళీ ఇంకా మెసేజ్ చేశారు సార్ ఉంది.
ఓకే. అది కాకుండా ఓవరాల్‌గా ఎంతమంది ఇవ్వాల్సి ఉంటుంది? ఇప్పటివరకు ఎంతమంది ఇచ్చారు? ఏమైనా ఐడియా ఉందా నీకు?
ఇప్పటి వరకు ఒక్క 1 మినిట్ సార్. ఒక 15 మెంబర్స్ ఇచ్చారు సార్.
ఈరోజు?
ఈరోజు కాదు సార్, 2 డేస్ కలిపి.
15
అవును సార్.
అబ్బా! ఇంకా 50 మెంబర్స్ దాకా ఇవ్వాలి.
అవును సార్.
మరి మిగిలినటువంటి వాళ్ళు ఎప్పుడు ఇస్తారు ఏంటి? అది మీరు ఒకసారి ఎవరెవరైతే ఇవ్వలేదో వాళ్ళకి రిమైండర్ నోటీసులు పంపించండి ముని.
ఎస్ సార్.
పంపించి వాళ్ళు ఎప్పుడు ఇస్తారో డేట్ తీసుకోండి.
ఓకే సార్.
లేదా నువ్వే వాళ్ళకి ఏ నెంబర్స్ కి ఏ రోజున ఇవ్వాలి అనేది నువ్వే ఒక డేట్ ఫిక్స్ చేసి ఇచ్చేసే. అది నాకు కూడా పెట్టు. నేను ఆ రోజున ఎవరు ఇచ్చారో ఇవ్వలేదో మనం చూసుకుని దాన్ని బట్టి మనం సార్ట్ అవుట్ చేసుకుందాం.
ఓకే సార్.
అది బెటర్ కదా.
అవును సార్.
యా
సార్ నెక్స్ట్ క్లాస్ ఎప్పుడు సార్?
మండే మన ట్యూస్డే ఉంది కదా.
ఓకే
ట్యూస్డే.
అందరూ చాట్ లో పెట్టారా?